Okay. Yeah, so you make a claim about the population parameter. So you have a sample and you are making claim that in the overall population this will happen. In other words, we call it generalization. Okay, generalization. So the main hypothesis is called the null hypothesis, which is with the equal to sign, and the other one is called the alternative hypothesis, which is non-equal, and it could be greater, it could be less, it could be both. Okay, whereas the alternative, and our job when we are doing the hypothesis testing is to check if the null hypothesis is true or false. If it is true, the other one is false, and vice versa. Okay, so you can see it here. H naught is the one which we use for null hypothesis. Okay, and there is always a chance that the conclusion you are making could be wrong. Okay, so we have to set up a significance level up to which you will restrict yourself. Okay, that my claim is confident up to this level. Okay, the other side of the significance of the confidence level is the error. So if I'm 95% confident, that means I have a chance of 5% error. Okay, and the error can be of two types: false positive, false negative. False positive means that the null hypothesis was positive and you made it negative, or you rejected it. And the false negative is null hypothesis was negative and you accepted it. Okay, and you have to do the balance, okay, between them, and you have like keep the you have to keep like reasonable chances for both of them, because if you stay on one side, okay, then you may be either underestimating or overestimating. I think the example is given here in foundation design. A type 1 error, that means rejecting the null hypothesis when it is true. So the soil is not stronger than, so the soil is not actually stronger, okay, but you made the type 1 error and you said, no, soil is stronger. Okay, so if you try to correct it and you say, no, I will always assume soil is not stronger. So what you will do, you will do design heavier. Always. Okay, it's not 5%, always. Because you are going where? No, I will say soil is never stronger. Because I want to correct this error, right? That actually is not stronger, and I am accepting the alternate hypothesis. Okay, so if you just focus on one side, that means most of the times you will be over designing. Okay, and the other example was there's another example. There's no other example. Very good. So the other is that soil is weaker. Okay, and it will. So if you try to adjust one type of error, you will fall in the other type of error. So we need to do the balance. Okay, this is where we stopped, I believe, because we didn't want it to go into R at that time. Okay, so supplier claims that he has rebars, meaning rebars is what? Steel. Okay, steel bars. So he is claiming that the mean of my rebar, mean strength of my reinforcement bar is 500 megapascal, and he wants to take test 20 samples. Okay, or we want to test 20 samples to test his claim, his hypothesis. Okay, so we don't have the rebar data. Okay, so it's just creating random data. Okay, so we will create 20 samples from the software, assuming what was R norm. We used it earlier as well, last time. What is R norm? We used it in the previous slides, not here. Norm is normal distribution. Okay, and there was another one exponential as well, or not normal. Okay, so this will set a seed, meaning initial value. Setting the seed means initial value. Setting the initial value. Okay, so we are setting the initial value 5, and then we will start with the data generation. So we will generate 20 samples, 20 samples following the normal distribution, and normal distribution needs two parameters, mean and standard deviation. Okay, so since we are testing the hypothesis 500, so we are putting the mean as 495. We are doing it, okay? It's not actual data, obviously. You can put 400, no problem. Okay, then obviously that would mean that your hypothesis most probably will be rejected. Okay, 495 has a chance it may get accepted. This is why we are doing it. If you run, both of you would run this, you may get different answers actually. It can happen. Because this R norm will not be the same values every time you run it. Okay. So first thing is you have a histogram. This thing will create a histogram to check if the distribution is normal. Normal distribution means what? Again, we discussed it last time. It's a bell shape, right? And
it's the mean is value. The true value will be
in the middle. Okay, mean in the middle. Yes, symmetric. Okay. So are we getting this type of histogram? We should. We are generating the data.
Sounds exactly.
Yeah, not exactly. Okay. No histogram. It cannot be. Okay. So I think this happened last time as well, and we said that maybe one data set may not be normal, but if you keep on generating data sets after data sets, what will normalize? The data? The data? The mean of the data. Okay, so that was the main assumption. Okay, and did you get the t-test? You run the code, right? So it's telling you the mean. Mean is 487. Okay, what else? T value is -2 and the p value is 0.03. Okay, now you look here. Our null hypothesis is if the mu is equal to 500. Okay, and the alternate is mu is not equal to 500. Okay, we put the mean for generating the data less. Okay, so obviously we know from our data it will only go lower. It will only go lower. It cannot go higher. Okay, but let's say these are not generated 20 values. These are actual 20 values. These are actual 20 values. If I don't want to use this thing here, what should I use? If I don't want to use not equal to here, what is more important for me?
It's less than.
Less than 500 is more important for me, right? More, no problem.
Yeah.
More is good, right? More is good.
More is stronger.
More is always good, right? In anything, right?
Yeah, but it's over.
You need more from life, right? You need more time, more money, right? More stress. More. Why did you come to MS? You needed that, right? Okay. So we can replace it equal to that as well. But that also means that I'm checking what we call the one-tailed test. I'm just checking one side. If it's ours on the other side, I don't mind. Okay. Now what is the p value you got?
P value is 0.032.
Okay, which means 3% something, right?
Yeah.
Okay. And normally we take the significance level or the error value up to 5%.
Which is low.
Okay. So this is less than that.
So it's acceptable.
Okay, it's acceptable. Okay. Acceptable is what? We're rejecting the null hypothesis.
Yeah. Because it's less than 500.
Less than 5 days.
So we're rejecting.
We are rejecting the null hypothesis. Okay. Clear?
Yes.
Okay. What did you get? What is your mean? You have the slides?
Yeah.
What did you do? it's copied the first line as well. Just do up and delete this.
Should I paste it again?
Enter. No.
Let me copy.
Okay. Now you see your mean is, her mean was 487, right?
Yeah.
Your is 477.
It's because it's generating random 20 numbers.
Yes. Okay.
That's fine.
So if you increase the sample size, you will get different numbers, and you may get a different result as well, and so on and so forth. Okay. So what we have seen here is a t-test, okay, but that t-test was comparing the value to comparing your data to a value. The value was 500.
Yeah.
Okay, we are trying to compare our value to our data to a value, and the value was 500. But you can apply the t-test to compare between two data sets. Okay, so you have data set with one admixture, and you have data set without the admixture. Okay, so now I'm not comparing against the value, I'm comparing if this data is equal to this data. Okay, t-test is more like the normal distribution. Okay, t distribution, or the t-test, or the t-value is by default assumes normal distribution. Okay, so there are two parameters which define normal distribution, right? It is in the code. When you did R norm, what two parameters you defined? The mean and the standard deviation, right? Okay, so t-test is also checking these two things, the mean and standard deviation. Mainly the mean, okay, mainly the mean. For standard deviation, in other words, the variance, okay, you know the variance and standard deviation. So for the variance and the standard deviation, we make an assumption. First assumption is they are equal. Second assumption is they are not equal. Okay, so t-test, when you are performing the two tests, you have to assume if the variance are equal or not equal. Okay, and this is an assumption. The t-test will work regardless. So it's your job to make this assumption. Okay, so t-test is based upon normal distribution. Normal distribution uses mean as standard deviation or variance. Mean, it is checked by t-test. Variance, your job. Check if it is equal or unequal. You have both options to perform the test with equal variance or unequal variance, but t-test will not check it for you. So if the variance were actually equal and you said they are not equal, the t-test will run, no problem. T-test will run, it will only compare the mean. Okay, and the results may change because you made a bad assumption. Okay, so variance is involved, but to check it is your job. Okay, so later on you will see the as I mentioned, the assumption is the data is approximately normal. T-test is based on normal distribution, and the variances are equal. If they are not equal, you have to mention it. Okay, and the third thing is what is mentioned in the first line. There is a third assumption. It's not written here, but it's mentioned in the first line. Data is independent. These two sets are completely independent of each other. Then you can check it. Okay, but for example, if you are checking compaction effort, okay, or compaction level or density, okay, so you compact the soil in layers, okay, and now you are checking if the compaction of the first layer is less than the compaction of the second layer. They are dependent, right? If I don't do the proper compaction of the first layer, the second layer obviously will affect it. Okay, so these are dependent data sets. I cannot compare them. Okay, so t-test is for independent data sets. But if you took two data sets which are dependent and did the t-test, you still get an answer. Okay, but can I trust that answer? No, obviously. The point which I'm trying to make is when you are using these techniques or those techniques which you are learning in AI, there is a certain thing which you have to take care of yourself. You cannot rely on the model to tell you everything. Okay, whether it's an AI model or something like model. Okay, yeah, with AI we have more flexibility, so you will not see these assumptions with AI. So somebody applied some AI modeling technique or some AI thing, clustering for example, and they check if there are two clusters of data or not. Two groups means two clusters. They checked it, and the technique shows that there are clusters. Okay, but you didn't check that these clusters are dependent upon each other. Okay, for example, I showed you one time the data about, and I showed you the graphs and all, everything for solar panels. Okay, they are trying different molecules, combining them to make the solar panels. Okay, so I was trying to improve the accuracy. The last run I did, the accuracy was not good, but they were happy. So, yeah, exactly what we want. A bad model. But anyways, so I didn't know that we would be happy. So I was trying to improve the accuracy, and I was, chatting with my friend, daily, right? So it told me that okay, you have two parameters. Okay, they call it homo and lomo. Okay, let's say H and L. I said, how can I improve the accuracy? He said, add more features. But from where do I get more features? He said, one of the features is these are two inputs. I said, oh, add more features. How can I add more features? He said, add this. Add this. Another feature is if I put these two features in the model, they are already there. Will this make any difference? If there is an effect of H and L on the model, or H and L on my variable, then H minus L or H and L separately will make the same difference, right? It will have the same effect, because in the end, what is this? H and L. Whether I subtract them or I put them one by one, doesn't matter. It's a model. Okay, but the point was that it kept on showing me these, and it kept on giving me code. Okay, that see, you don't have to do H minus L yourself, H upon L yourself. I will do it for you. I'll see, this is the code, and I have to stop it and say. But these are, if I'm putting H and L in the model, H minus L will not make any difference. H upon L will not make any difference. Okay, but these are the same variables. Okay, then I said, yes, you are right. Okay, so anyways, going back to the point, the models and AI and tests, they have some assumptions, they have some limitations. They will not check it for you. Okay, they will not. There are very few models which will give you the green flag. Okay, and even in order to understand that green flag, you must have an understanding of the problem you are having. Okay, I'll give you another example. I believe I deleted the data, but I'll check for you if I have the data. Come on. Yeah, I have it. If you are looking for a model, you know about R square, right? R square of the model. Okay. So it ranges from what to what? 0 to 1, right? Which one is best? 1 is best, right? is the second column. And this is on the test sample. The test, not on the training one. And you see all of them. Either they are 1, 999. Okay. Should I be happy? Yes, right? 2 minutes of happiness. This shows that your data has a problem. It's impossible. Okay. So the problem was, then we consulted them and we told them that this is what we are getting, and this could be the reason. The reason is that value is like I hide this and I give you the value of this. Okay, so this is 2, this is 5, and I give you 3. And I say, okay, use these 2 and predict this one. Any model will get this. Okay, and if you got this relationship, will you get 100% accuracy or not? Either. Whether the test sample, what was the problem? This value, the answer is calculated. You are recalculating the calculated thing. Okay, you are trying to put an equation over an equation, or trying to estimate an equation which already has an equation. Okay, if this value 3 was taken independently of these 2, then I make the model. I will never get 0.999 accuracy because this value is taken independently. Okay, and going back to the assumption of normal distribution. Why normal distribution is a distribution? Why it's not a straight line? You always get this value because there is an error. Okay, real world has an error. Okay, okay, we already discussed this. Okay, you already have the concrete stamp data, right? And you have the read command. You need to send it to me in the read command. You keep on sending it to her. So I can correct it in my slides. Okay, so this this program will check the or will perform the t-test between the 2 mixes. You have the mix A and mix B, right? Okay, so this will perform the t-test between mix A and mix B and check if they are equal or not. The mean of the 2 mixes are equal or not. Okay, so it will plot a box plot. Okay, I got it, thank you. And it will do the t-test. So the box plot can tell you if they have equal variances or not, like it will give you an idea. Okay, are they normally distributed and do have then after that it will come on. To put the hash. Okay. Is it in the folder? There's an in. There is no in this code. Now where is the in? True, and then after there's an extra hash here. Okay. In file yeah, directory again. And then
some wrong.
Yeah, it will only show the folder. Yes.
Okay. The session. Go to session.
Yeah, same.
Choose directory.
Directory. No, because there. Click here. Yeah. Okay. Now go. It's running something in the background.
It's not working. Did you fix the link?
Where is it? Which one? Is here? Okay. Just assign also? No. Okay, data open. Open. Concrete strength data. No, no. You have the data concrete strength, right? Yeah. Just click on it. Okay. Open. You can restart and then set the directory first.
Okay.
Directory where exactly the concrete data is. And I believe it will take the CSV file, right?
Yeah.
That is CSV. So you need to check if the concrete strength data is CSV or not. Did it work for you? Okay. So the variance is the size of the box. Okay. Obviously you can see the
Range or
no, how much variance you have. So if you feel it's not equal, you can just change it here. Variance equal from true to false. Then it will.
it did not change.
Same values. The degree of freedom has changed.
This changed. 50.
Yeah. The p value is
The value is closer to 4. No.
it's still zero.
Still 0.
Still zero. Okay, but there's a change, obviously. This is the mean of the two groups. Obviously, it will not change. Okay. But when you change the assumption, the p values and the t values they change. Okay, degree of freedom and everything is changing. Okay, so the point is the assumption can change. In this case, the change in p value and t value does not change the result. But in some other case, it can change. Yes. What happened?
Unexpected.
And CSV file? Yeah, okay, CSV. No, you have to like, if you keep on entering, it will keep on going to the same code. You have to like copy and you have to paste it again and run it again. First, take the read. You can take the read from the last. Now don't enter and first check. Okay. No, shift enter. Okay, now put the rest of the code. Okay, now wait. Okay. Okay. Same box, right? Yes. Okay. We only have the box plot, but if you go and you can do the there was something about the histogram, right? You can use the histogram command to check the normal distribution as well. We only check the assumption of the variance. From the box plot, you cannot see if it is normal distribution or not. But if you do the histogram, you can check if it is normal distribution or not.
We can do both in the same code, or we can do both, or it has to be.
Yeah. But it has to come after the read.
Okay.
And what else? How was the box plot? Because the histogram will so you have to like specify in the same way, okay, the columns, because you want histogram for each mixed type, right? You don't want it for the whole data. So data has two mixed types. No, if you go there, just change the box plot to this command. You have the box plot, right? Yeah. Okay. No, then you have to do the data.
Yeah.
Maybe we did the histogram for each one separately earlier.
Maybe we need to call it, or
No. We don't call it. But maybe
here
we did histogram earlier
yeah.
in some other. No. But this histogram is for the whole data.
Oh yeah.
We are trying to do it for each mixed type separately. So there must be some change. Okay.
Maybe we have to
If you go back to the previous slides, you will see the histogram.
mix A and mix B maybe separate, or
Yeah, but still we need to let the code know that mixed A and mixed B is one. Anyways, you can check it later on or just Google it, no problem. Okay, this is, we have a city which is claiming a new traffic management system reduces the average commute time. We need it very badly, right? A new traffic management system which will reduce our commute time. You remember a couple of days ago there was a big traffic jam in the morning all over Bahrain, right? They said a truck was overturned there. On the, you don't go office in the morning.
but not the center.
No. It was Rifa and Ubli and Adliya, so many areas were blocked.
Diplomatic area.
But this truck was on Sita.
I could
This truck was on surprise.
because
But so many areas were blocked.
I know it was fun.
Okay. I was also fine. I was just going there, but I said it's going too slowly. I took a wrong turn and then
Yeah, we stayed
1 hour long.
1 hour
7, 6:50. 6:50 to 9.
Oh my god. That's 2 hours.
2 hours with my 2 daughters.
So I was taking
Double
them to
torture. Once they were saying,
So they were late
we
to
we are not going, we are not going, we are not going. And then, because they were saying, so I took the U-turn, okay, I will take another way. And then, Baba, why are you staying here now? I cannot go.
And this is even worse.
Yeah. Baba, will we find traffic ahead? Will we find traffic ahead? Will there be traffic on the next road? No, no, inshallah, no. No, no. And near your school, there will be no traffic. But the school is Sitra. Anyways, so we have two claims here. One claim about traffic management system, reducing the commute time. The other one about a researcher who believes a new geotextile will increase the bearing capacity of the sandy soil. So they put this membrane on the soil and it is supposed to improve the bearing capacity to hold the soil. Okay, do not let it slip. For each scenario, you define the population parameters, you define H0 and H1, and you have to specify which one is one-tailed and which one is two-tailed. Okay, one-tailed is you are just checking one side. Is it greater or less? Two-tailed is you are checking not equally. Getting my point? Two-tailed means I am checking if it is equal or not equal. If it is not equal, whether it is higher or lower, it has same meaning for me. One-tailed means that I am just checking if it is higher or just checking if it is lower. Okay. So for the first one, they are claiming a new traffic management system has reduced the average commute time. Okay. So what are my population parameters?
The goal, it's reduce average.
No, population parameters means what?
What
We discussed it in the last lecture.
we are measuring.
What we are measuring is
Just time.
time, right?
Yeah.
Okay. We are measuring commute time, right?
Yeah.
Okay. So our population is what?
The users or
The commute time for the users, right? Okay. The commute time of the users, all the users?
no, the highway or
The users
specific
on the highway where I applied this new traffic management system, right? All the users on this highway where I applied the new traffic management system. Okay. So this is my population. Commute time is my parameter, and the entire population comprises of the drivers who are going on the highways where I applied the new traffic management system. Okay. What is my H0 and what is my H1? What is my null hypothesis? What is my alternate hypothesis?
none is that it's reduced.
Huh?
None that the time is reduced.
Null is the time is reduced.
Yeah.
Will work. Don't trust her.
No, I'm thinking. Null is maybe in this theory about the same system succeed with reducing, yeah, the same.
Don't trust her.
Yeah, I know, but
It can be anything, it depends on what you
think. Or maybe it's not.
Null always has what?
equal.
Equal.
So it's reduced.
How can reduce be equal?
Same.
Same.
Time. Yeah.
Null hypothesis is the new traffic management system has no effect on traffic time. No effect on commute time. No effect means what? Before and after will be equal, right?
Same.
Okay, so this is the null hypothesis. Okay, or to be more exact, has no effect on reducing the commute time.
Maybe it increases.
Huh?
It might increase or
Where it might increase. But in any case, it will be useless, right? If it is increase or equal, the investment is useless. Okay? So if I say that the new traffic management system has no significant impact in reducing the travel time, says everything. Okay. And what will be the alternate hypothesis? Alternate is just we remove the word not. We said the new traffic management system has no effect in reducing the. So if you reduce, if you
Has reduced.
yeah, has significant effect on reducing the travel time. Okay. Now is it one-tailed or two-tailed?
One tail because we're assuming it's reduced.
It's reduced. Okay. So we are only looking for less than. Okay. What about the second one? A researcher believes a new geotextile increases the bearing capacity of the sandy soil. What are the population parameters?
Bearing capacity.
Bearing capacity of
Sandy soil.
all samples of sandy soil, right? Bearing capacity of all samples of sandy soil. This is my population parameter. Okay. What is my H0? What is my H1?
H naught is that it has no effect. Same.
And it should be there is a fact.
Say again.
Same, no effect for H naught.
And it should be there will be
H will be increases. H will
Has significant effect on increasing the bearing capacity.
one tail increase.
Yeah, in the one tail. Yes. Okay. Because both of them are one tail. And you got a writing like bad people. Done?
Yeah.
Okay.
Yeah.
Why don't you guys like do a competition? Who writes fast? It will be a good study. You are writing on paper. You are writing on this.
I don't like writing.
Next lecture.
Huh?
I don't like writing.
Because you're
Yeah,
not
that's
used
why
to
good
it.
study.
I'm
Yeah.
not used to it.
Yeah, yeah. Me too. I haven't
Maybe I'm
used it.
old fashioned.
Yeah. My daughters come and they start doing this on my laptop. Their mother has a laptop which has
Touch.
touch. Right. It was supposed to be my laptop, but she took it. Anyways, why don't you come up with an example of a two-tailed test? Both of them are one-tailed, right?
Yeah.
Why don't you give me an example of a two-tailed test?
Maybe we can go with the concrete
Think.
structure.
Go into deep thinking mode. Okay. You can discuss with each other. I'll go and get water. Okay. When I come back, you give me one answer, both of you.
For the coefficient, is it introduce increase with the number? property أو ناخذ واحدة من البروبرتيز حق شيء
أو مثلا water demand.
certain
Water demand.
okay the population
Yes, tell me. Still discussing? Okay.
We can just change the K
Mm-hmm.
and then it will.
It will not make any sense. You are applying something new to do what?
Effect.
To check if it is equal or not.
Yes.
Only? Doesn't make any sense.
Maybe something natural. Something natural. It's, or
Like what? Maybe when you are doing your own research, you have a problem, and you are thinking it is two-tailed, but it is one-tailed. So if you cannot come up with a thinking process, will help you to distinguish between two-tailed and one-tailed.
yeah.
This thinking process.
Maybe objective generated analysis. Time effect on time. Idea generation. This is a question once again. You can just claim that it has an effect without stating. So effective.
In which case you will just check if it is equal or not equal. Two-tailed means what? You are just checking if it is equal or not equal. Right? Greater or less doesn't matter for me. What case could it be?
That our null hypothesis is equal.
Like in like practical sense, where would I be interested in knowing if they are equal or not equal only? I'm not looking at the type of effect.
The example of strength, for example, strength of the cell. If we have the value, or if we have, for example, we're assuming it's equal to the mean, like the one we did
Okay.
previously.
Okay. If you are checking against a value,
Yeah.
you're checking against a standard maybe.
Yeah.
Okay. This could be. Anything else about data sets? In data sets, if you're comparing two data sets and just you are interested in if they are equal or not equal.
Two data sets.
Yeah. This is we're talking about two data sets, right?
Yeah.
One before and one after. One with geotextile, one without geotextile. So these will be two data sets, right?
Yeah.
Not a data set and a value.
Mm.
So this is an example of one-tailed set for two data sets. Is there an example of a two-tailed test between two data sets? What the example which you gave is between a data set and a value.
Yeah.
Maybe introducing new material in the concrete mix usually consider like a 2D.
Introducing what?
A new material to enhance the
Yeah.
Composite.
Yeah. Yeah.
Hybrid.
And compare.
Yes.
Estimate.
Yes. You mentioned about fibers, right?
Yeah.
Okay.
Steel.
So we have, for example, steel fibers and we have bamboo fibers.
Hair fiber.
Okay. You can check if there is an effect of the type of fiber or not.
Yeah.
Okay.
Compared to the
If I change the type of fiber, is there an effect or not? First of all, then I will see whether it's higher or lower. But is there an effect? Okay. The load on the speed, is there an effect? Okay. Or what else? I believe there's another example. For example, the grades of the students. Okay. The grades of the students. Okay. Test 1, test 2. Is there a difference between them or not?
which one is lower, which one on average?
Yeah. I'm not looking for which one is higher or lower. I'm looking for is there a difference?
Yeah.
Is there a difference? Okay. Because I took test 1 from chapter, I did this. In one of the research, I did this.
You're not claiming that.
I'm not claiming it is high or low. I'm just claiming that it has an effect. The time of the test has an effect on the scores.
Yeah. But I'm not claiming it's negative.
I'm not claiming it's higher or lower. I'm just saying that the first exam, it happens in start of semester. The second exam happens in the middle of the semester. Okay. So does this change in timing have an effect on the student scores or not? Okay. Or the first exam has chapter 1, the second exam has chapter 3. Okay, so is there a difference in the performance of the students with regards to these two chapters? Okay, so then I will later on, obviously, I want to look at what is the difference. Yes. Okay, but now, right now we are just saying, okay, is there a difference or not? Okay, another example is the pollution levels. Okay, so more example, if you have wastewater. Okay, so is there a difference in the pollution level in the soil, okay, which is around the channel, okay, with respect to depth?
Yeah.
Okay, is there a difference or not? Later on we will see which one is higher or lower also. Okay, so
for the second one, we can also change it to two tables. If
we can
a researcher believes that a new geotextile affects the bearing capacity.
affects it, yes.
It can be two tables.
Okay, but these two cases, we are doing something which is supposed to have a change in a particular direction. Okay,
Assume.
but yeah, but for the case of pollution, for the case of student grades, okay,
We don't.
I just, yeah, we don't know, and we are not claiming anything that it should be positive or it should be negative. I'm just claiming that there could be a change. Okay, so two-tailed, where you are not claiming the type of effect, you are just checking is there an effect. Type will be checked later on. Okay, once you have done the hypothesis testing, t-test is one type of test you can perform for the hypothesis. It's not the only one. Okay, so keep this in mind. There are different methods. We will discuss them in the coming slides as well. There are different methods to check the hypothesis. T-test is one of them, very common. You can use it to check against the value. You can use it to check against two independent data sets. You can use it as one tail, you can use it as two tail. Okay, but this is not the only way. But let's say you have performed the t-test and you found that there is a significant effect. Then it must be written in this way. Okay, this is how you write about testing of a hypothesis scientifically. Okay, so two sample t-test was conducted to compare the mean strength of mix A and mix B. So what type of test you are performing?
T-test.
What are you comparing and for what? Two types of mixes. Okay, there was a significant, so this is the conclusion now. There was a significant difference in the mean strength between the two mixes, and then you are supplementing your answer with the values. So why we are saying there is a significant difference? Because the t value is this much and the p value of the t is 0.001. Okay, so that's why I am saying there is a significant difference. Then you provide more details about the data itself. So there is a significant difference. But what does it mean? The mean strength of mix B is 47.2, standard deviation 3.8, was significantly greater than mix A with a mean of 42.1 and standard deviation of 3.5. Okay. Type of data, what you are comparing, type of test, what you are comparing between what? Result of the test. And then more information about the data. Right? Now you see, this is like mix A and mix B from our concrete strength.
Yeah.
Do I know what is mix A?
No.
We have to reform it.
We did, somebody did, right?
Yeah.
Do we know when we are performing the test? So we are not, it's not one tail, because we are not claiming anything.
Yeah.
We cannot do the claim now.
We don't know which one is better.
Which
We
one is
just
better?
compare.
Okay, so it's a two-tail test. Okay, it's a two-tail test. We are saying, okay, it has a difference. Okay,
So what's the difference between mix A and
We don't.
okay. First thing is there a difference?
that's
Okay,
the
is there a difference? Now, once the t-test was performed, it found that there is a difference. Now you go back to, why is they are saying it's significantly greater? Because of the values.
the mean.
Okay, so this is how you modify or you extract the result and then go to another extent to explain your result. So this test did not say that it was significantly greater or lower. This test only said it has a difference. It has a difference.
Our interpretation.
But if it is a difference, if there is a difference, and I see one mean is higher than the other, that means the mean of mix A is higher than mix of B. Alright?
Yeah.
Okay. But the main thing is you need to look at the pattern. Okay, how this thing is reported, and this is how you should do it. Okay, and this is the main lacking when we are writing the scientific reports. Even at my end, when I am writing the results in the reports, we keep on saying table 2, table 1, figure 1, figure 2. Okay, yes, you mentioned it somewhere here. Okay, that as per table 1, but then you provide the reader the complete information. Okay, so he doesn't have to do this again and again. Yep. Okay, so this is what you will do in the end. Okay, we have a pH value or local river is 7. You take 15 samples, perform 1 sample t-test to test this claim. 1 sample should be 1 10.
We don't need the standard deviation for this.
Sorry,
Or should we assume?
I'm supposed to give you this data.
We did.
You don't have it?
It's not in the
Okay. Anyways, I will check. I will give the data, no problem. Okay, so you will check the data, you will check this claim, and you will write the null hypothesis and everything, and you will write it in this format then, in the end, the result. Okay, showing the full information. So you write it in the R and you will give the full information, and then you do the same thing for your thesis topic. Okay, the proposal, not the project, the proposal. Okay, so you develop your null hypothesis and alternate hypothesis. It can be more than one. It can be more. You get my point.
This is based on the first homework, yeah? This is
Yeah.
thesis.
For 1 and 2 are same, and the third one is related to your proposal. Okay, but what I was saying was you may have more than one null hypothesis in one topic. Okay, and for every null hypothesis there is an alternate. It's a set. Okay, so you cannot say I have 3 null hypotheses and 2 alternate hypotheses. It cannot happen.
So minimum 1.
Minimum minus 1. Yes, 1 at least, yes. And this, like you were showing me for the term project, this is like a research question. Okay, the hypothesis is just a research question. Okay, so you have to think about what is my research question. Okay, and then you will write it in the form of a hypothesis. Okay, but I was saying that you may have more than one null hypothesis in your topic. Okay, but you will have equal number of alternate hypotheses as well. Because for every null, there is an alternate. For every negative, there is a positive, right?
Yeah. And later on we have to prove it or just.
No, we are just at the proposal stage. This, for the topic, thesis topic, you are just developing the proposal. So proof will come later on when you are done with the research. Okay, if you can prove it now, then
But not this
No,
course.
I mean later on.
later on in your life,
Not in this course.
not in this course. If you decide that you will go along with the same topic and same
In the
proposal,
master.
then yes. Just to give you the head start, and the main aim of the course is so that you, in the end, you are able to at least go up to the proposal stage. Okay. And we're doing the term project so that you know how to do the whole problem solving yourself. Okay, so let us pray and then come back. The only time we get is for scrolling, right? So we have another problem with making multiple t-tests. So with every t-test we have a possibility of error, right? We have a possibility of error. So when you will make the final conclusion, for example, the conclusion for the difference between a roundabout signal and stop sign, you are making how many t-tests you will make? If you are comparing 3 groups of data, how many t-tests you will do?
6.
6? 6? Okay. Each one of them has a percentage error, right?
Yeah.
Because we are checking 95%, so each one of them, or whatever, 90% or whatever, we check.
So 5%.
Okay. So each one has 5% error, right?
30%.
Uh,
The total.
no, not 30%. Something else, right? 30, 10, something else. It's written there, okay? But the point is, in the end, you will make the conclusion about the whole sets of data, complete sets, 3 sets of data, right? On the basis of 6 tests, okay? When you combine errors, okay, when you combine errors, they are added or in this way, okay? So 1 minus 0.95 is, you know, 0.05, right?
Yeah.
0.05. Okay. So each one, if you are doing 10 t-tests, okay. So this will be to the power 10, okay, because each test has a significance level of 0.95. Okay. So when you will combine them, you will not add them. Okay. This significance level will not be simply added, because you cannot. Can you add 0.95 plus 0.95 plus 0.95? We cannot. Right? So you have to take the power. Okay. So the errors or the significance levels are added in the form of the power. Okay. So for one test, I was having a significance level of 0.95. For 10 tests, I will have a significance level of 0.95 to the power 10. The combined.
Which is 40%.
40%. Okay. So the error, the significance level dropped from, you did 1 minus 0.95 to the power 10. So the error, 0.95 was my significance level. Okay. And for 10 tests to the power 10. Okay. And why I'm still subtracting with 1?
Because one is perfect.
1 is the perfect, or 1 to the power 10
Is
is what?
10.
1 is square is
Is 1.
1 to the power 10
It's
is
always
1.
1.
Right? And yes, in the end, I'm looking at the 100% possibility for the complete sets of data. Okay, they are calling it the family of data. It's no longer a pair, it's a family. Right? A pair is not a family. You have to have kids. Okay, so that's why.
2 or more.
More. Two as a pair. Okay, pair. Okay, the pair is not a family.
So 3 or more.
Okay, so but you get the point. We are doing multiple tests, but in the end, we need to combine them to make the conclusion about the entire family of the data. When you combine them, you are combining their errors. Okay, and errors are combined using the power rule. Okay, there is another name given for it, which is called the what do you call, if this happens, then what is the probability of this happening?
The opposite.
No. Conditional probability. Conditional probability. So you are applying conditional probability. If A is equal to B, then what is the probability that B is equal to C? And if A is equal to B and B equal to C, what is the probability that C is equal to D? So this is called conditional probability. So when you apply, so when you will make the conclusion about the entire family of data, you are applying conditions on all these 10 sets. So that's why we are applying the power rule. Okay. If these are 10 independent sets, and I look each one of them separately, then each one of them has an error of 5% and a significance level of 0.95. There is no power rule here. Okay. But now I say that all of them combined together have this result, then I'm applying a conditional probability. Okay, so the conditional probability, you have to apply the probabilities are added using the power. Getting it?
Yes.
Clear? Yeah.
Yes.
Okay. So in this case, then we have to adopt the ANOVA. Okay, ANOVA is the short form of analysis of variance. Analysis of variance. Okay. You can see the difference between the t-test and the ANOVA from the name. What we were comparing in t-test? The mean.
Yes.
ANOVA is analysis of
Variance.
variance. Okay, so we are comparing the variance. Because of the checking of the variance, ANOVA keeps the error rate same across all the groups. Because it's not checking for the mean, it is checking for the variance. Okay, and how does it check for the variance? I will show it. And again, you will be using R, you can use Excel as well to do the ANOVA. Okay, but the main concept of ANOVA is, so we have, for example, 10 groups of data, 10 different types of concrete samples. Okay, you take one type of concrete sample, these are 30 values, let's say. I can calculate the variance of these 30 values, right? I can calculate the variance of these 30 values. Okay, so for each group I have a variance which is in the group itself.
Yeah.
Which is in the group itself. Okay, and then I have a variance which is across all the groups.
The variance of the
Uh-huh.
variance.
Not the variance of the values. Variance of all the samples combined. It's not the variance of the, it's not like you, okay, I have 10 values of variance now, take the variance, no.
So
It's the variance of, we say that each has 30 samples,
so
I have 10 groups, variance of 300 values. This is what we call as the variance across the groups or variance between the groups. Okay, so there's a variance within the group, there's a variance between the groups. Okay. ANOVA says, or the theory behind ANOVA is that if the difference between the overall variance and the group variance is small, then we say that it's basically the same.
So
All groups are same. All groups are same. Based on the variance. Okay, so whatever variance I am getting across the groups, if it is the same as the variance within the group or close to it, then all groups are same. So whatever is the difference between the groups has no effect on the values. Okay, so they were different concrete samples because you were using different sizes of aggregates. So if you ANOVA detects that the variance within the group and the variance across the group is the same, that means the size of the aggregate did not have any effect on the concrete strength. Got it? And the vice versa. If the overall variance is something and the variance within the group is something different completely, then whatever the difference between the groups has significant effect on the value. Okay, so it compares between groups to variance within the group. If group variance is significantly larger than the within group variance, then the group means are likely different. So it's saying because if the variance is different, then the mean will automatically be different. It's like inherent. Okay, so for example, I am saying that I have this value. Okay, maybe the range, whatever value I have. So I have a chance of, for example, take your travel time. Let's say if I go from this highway, okay, my travel time is X value, but I have a variance of only 2 minutes, plus minus 2 minutes. Okay, if I go from this highway, okay, my values are these, but here I have a variance of plus minus 10 minutes. So even if the range of value is same, because of this large variance, the mean will automatically be different. Okay, because I told you mean is what is mean? Most expected value. So when the variance becomes greater, the most expected value is itself. Okay, it will automatically shift. Okay, so the same goes here. Okay, so in the t-test we were comparing mean and the variance was what? Not what? Variance, zero variance. Huh?
We only consider the mean.
You only consider the mean, but what did we say about the variance? We did the t-test. I made you do both ways.
The difference between the mean.
About the variance. What about the variance? What was in the t-test about the variance? We put the value. We made the assumption. We did the box plot, right? So you see the box plot, variances are equal or not?
Yeah.
So variance is your assumption. Okay, variance is your assumption. Or variance is something which you fix yourself. Are they equal or not? But you're checking the mean. It's the reverse here. It's checking the variance. On the basis of variance, it is making a conclusion about the mean. Here. Got it? Okay, and I told you the logic. The variance goes higher, the most expected value will flutter a lot. Okay, and so on and so forth. So, for example, they have given, and this is related to the question which I asked you, in what cases you are doing the detailed test. So, this is an example here. So, they measure the heights of players who are playing different games. Okay, basketball, soccer, and who are doing gymnastics. Okay, my wife says basketball players are taller. So, she tried to send my daughters there. But my daughters being my daughters is not good. Okay, which is good. Otherwise, they could be taller than me. Then who needs them? Okay. In this case, there are three groups. Obviously, if you do the t-test, you will have the same problems: the conditional probability and the error multiplying. So we can do the ANOVA. Okay, ANOVA will tell us if the differences of heights, the variance of heights within each team is very, very low as compared to the overall variance, then we will say that the sports affects the height. Okay, and again, for ANOVA you cannot claim one tail. Because there are multiple groups, right? How can I claim? I cannot claim. Okay, there are other tests to check that. Okay, so this is what they are saying here. Okay, so the ANOVA hypothesis is slightly longer and complicated, but you can see null hypothesis, all of them equal. The null hypothesis, mean of one group is equal to mean of second group, and the third group, and the fourth group, all of them are equal. Null hypothesis for ANOVA is always, obviously, all null hypothesis has an equal to sign, but ANOVA null hypothesis has a longer equal to condition. Okay, all multiple means, whatever number of groups you have, k is the number of groups you have. K is the number of groups you have. 3 groups, mu1 equal to mu2 equal to mu3. 10 groups, mu1 equal to mu2 equal to mu10. Okay, and the alternate hypothesis is any one of these equal is not equal. Anyone.
Which means our hypothesis is rejected.
Null hypothesis is rejected because null hypothesis can only be true if all of them are equal.
We cannot extract this.
Right now we don't.
Because if one is not equal, this means that one sport affects the other.
Yes. If any one sports affects my wife's hypothesis, okay, that basketball will make you grow taller. Okay, have you tried it?
Yeah,
No?
But it's an
No,
assumption.
yeah, assumption. Anyways,
But it's false assumption because I'm still short.
you try it. Okay. But the point is, if any of the mean is different, then it will reject the internal hypothesis. Okay. So the alternate is at least one is different. At least one has a variance within the group much less than the overall variance. Okay, and just to explain, because we've already written here the between group variance is significantly larger than the within group variance. Okay, it's always this case or equal. It cannot be less. Getting my point?
So if it's larger, it's still okay, we're accepting that they are
No, we reject the hypothesis.
still rejected.
We reject.
It should
If it
be
is larger,
if it's larger.
if the overall variance,
It's
if
significant.
the overall variance is equal to the variance within the group, is equal to the variance within the group, almost, we accept the hypothesis. Okay. If it is larger, we reject null
If it's
hypothesis.
lower, we reject.
Hmm?
If it's lower, we don't reject.
It cannot be lower.
Okay.
If it is lower, there is a problem
There's a problem
in the data or the calculation. Okay. Why? Because you see, you have 10 groups. You have 10 values in each group. Total 100 values. Okay. So if your variance for 10 values is more than the overall variance, which includes these 10 values, you have a problem. Okay. The between group already has these 10 values, right? So if I plug only a part of these values and calculate the values, it might be smaller. It can be equal, but it cannot be larger. Get my point? Because these 10 values are part of this set. Okay. So this is what I wanted to emphasize, that ANOVA says that overall variance can be equal or larger. Okay, cannot be lower. So it will not make any sense. And again, we have the same significance level, 95%, the error rate 5%. Okay, and given example given here, the shear strength for different bolt types A, B, and C and D is the same, and the alternate hypothesis is not the same for all bolt types. Okay, the assumptions behind performing the ANOVA, these are the assumptions. The first assumption is the observations are taken independently within the groups and between the groups. Okay, what does it mean? That the between the groups assumption is the same as the t-test. Okay, if you have two sets of data, they are taken separately. They don't, one data set does not affect the other. And I gave the example of the compaction. Okay, so two layers of compaction are not independent. Okay, so they cannot be tested. Same thing with ANOVA as well. If you have 3 or 4, for example, bolt types here, okay, then all of them should be independent of each other. Okay, and within the groups they also should be independent. Again, same thing with the t-test as well. So if one group has 10 values, all these 10 values should be independent of each other. Okay, it's not like you are saying that I'll take, for example, traffic volume. If I'm taking traffic volume for 10 different hours, and these hours are in succession, okay, then they are somewhat dependent upon each other.
Because if it's congested in the previous.
Yeah, the previous hour is congested, the next hour will not be like 0 or something. Okay, you can do it on different days maybe. Okay, without succession.
Discrete.
Yeah. Then the data is normally distributed, same thing. Okay. Homogeneity of variance. The variance within the group is roughly, within each group is roughly equal. Okay, same thing which we did, which we said for the t-test. So we are saying variance of group 1 is x, variance of group 2 is also somewhat x, 3 is also somewhat x. But if I combine them, it could be greater than x or equal to x. Okay. But within the groups, it's almost the same. Okay, ANOVA is generally robust to slight variations of normalcy and equal values. Okay, so it can still work if you are a little bit away from the normal distribution of the variance, or the variance are a little bit different from each other, or 1 or 2 of the groups have different variance with the others are. So it can still work. Okay, so ANOVA works on a very large range of data. Okay, it's not very strict. Okay, and especially with the balanced sample sizes. Okay, so if you are doing experiments and you are taking, for example, 3 samples of each type 5 samples of each type. It's a very small sample size, but it's balanced. So ANOVA can still work. Okay, nobody, you will see a lot of literature, lot of research in which ANOVA has been used. Okay, on very small samples with multiple groups, and you will not see any problem with this particular aspect. Okay, nobody says that no, you have to check the variance, and you can actually see the variance is not equal because 3 values, the variance can rapidly go up and down. The 3 values is what? 1 value is static and it's an experiment. Okay. So it's very easy in an experiment for 1 value to go very high or very low because of anything. Okay. You made a mistake in looking at the value. Okay. It can happen. Who can check later on? It's gone. Sample is gone. Okay. So variance does go very up and very down. Obviously, with 3 samples, normality is not in the question. Who can say that these 3 values are normal distribution? Nobody can say. Okay. But ANOVA is still applied and nobody argues. Okay. And if they are not arguing, we don't have any problem. We don't know why they argue. Getting my point? These are statisticians. We don't know why they come up with this 0.05% and so on. Okay. So if they are happy, we are happy. No problem. Okay. But they say that it's mainly that the ANOVA is more robust. Okay, I did not include it here, but later on I will show you the regression. The equation of ANOVA, if you search for equation of an ANOVA, the form of ANOVA, function of ANOVA, and the function of regression model is almost the same. Okay, this could be one of the reasons. Because regression equation works irrespective whether it's normal distribution or not. Nobody says you have to be a normal distribution and the variance should be equal. Okay, so yes. Okay, how can you check the normal distribution? You can plot it. You already seen the histogram, right? Okay, and QQ plots basically tell you the distribution, like the bell shape. Okay, how much percentage in each, the central limit theorem I told you. Okay, the QQ plots can tell you about that. And how would you check the equal variance? You can do the box plot. You already did the box plot, and you can do the Levin's test as well. It's a test. It's not a plot, it's a test. Okay. So this is again bold strength data. Did I give it to you? The bold strength data. Yeah. So make sure you are in the same library. Your directory is the same, and then you can use this. And I believe you have to install this car. Because they are calling the library, that means it should be installed as well. Okay, so you have to like use the install command or something. First check if it works.
Cars, is it?
No, it's giving the cars meter. Okay, just run it. Let's see.
Car not found also.
Mm-hmm.
In library car there is no package called install. Oh, okay.
No.
Doesn't-
Install. You have to do the install first.
Install quotation marks.
Library. She's busy with the read command.
First the read command or
No, install.
here it's
Do
read
that
or
install.
string.